Next transform we're going to have a look at is view merging. So, and this is a little more complex example in terms of the statements we have. First one, we have a relatively simple view. Okay, we have a view called employees table, which is really, as a regular view, a stored query. We store it in the data dictionary. Then we can make simpler queries by just querying the view instead of querying the base tables. So in this view, we're going to pick a subset of the columns from the employee table, what their number, their name, job, etc. from the employee table, but we also want to limit it by just the members from Department 10. That's why we called it Employee 10. Okay, so we store this query as an object, and then we can do a select against the view, and it just means that the select becomes simpler. And when we do the select against, so we want the employees number, so we're further subsetting what's in the view, one of the 6 columns that are on the view. We're doing a further subset selecting. Okay, and we're also, so we're just selecting one column. We're also limiting the employee number further. Okay, and there are 2 possible ways for it to do this query. One way is to execute the defining select for the view, treat that as a result set, okay, and then use that result set, and the result set, once it's formed, doesn't have any indexes on it, okay, at all, as a row source. It's only the tables that have the indexes on it. And then execute the query against the result set, which implies it will have to do a full table scan of all the rows we return for Department 10 and apply this predicate to it. Instead of doing it that way, it can be transformed by driving this particular predicate, what was put onto the view, into the defining query, and then executed it as a query we did against the table. So to transform that, we take the original query in the view, this piece up here, which we restated down here. Now in here we were looking at a group of columns, so we can just drop the columns we don't want, because that's all we're querying when we queried the view. Then do it from employees, and we put the first predicate in, which came from the view. And then we end it with the second predicate that comes from the query on the view. Okay, and then we can optimize this. Okay, there is an index on this, we can use this, and usually the employee number is a primary key. We may, if it was a small enough range on the employee number, use the index on this side. We can AND, when we AND conditions together, we can use multiple indexes potentially, as long as we feel they're selective enough. Where up here, we only had the one index. When we did this, then we had no possibility of using an index, because the result table we get from executing the select is an in-memory table that has no indexes on it, logically. So it will try both ways and pick the one that costs out the cheapest. Okay. Next up is a transform for views called predicate pushing example. So we create a view that's actually a little more complex view. It's called ToEmployees table. We have ToEmployees table, employees 1 and employee 2. Maybe one is retired employees, one is active employees, maybe one is our original company and a new company we're purchasing, and we need to query across the 2 tables. We can create a view to do that using a union. All we're doing, and we're eliminating some of the columns. We're not using all the columns, or we could have just put a star in. So we're looking at a subset of the column, but we want all the rows from table 1 union with all the rows from table 2. And we're using the union operator. Then we're going to query this view, okay, our two employee table view, and we're going to have a predicate where we're going to limit the data from the two tables, employee 1 and employee 2, to just department 20. Once again, there are two ways. Execute the defining select, treat it as an intermediate table, and then apply the query on the view to the result set. So we get the data union, but the result set version doesn't have any indexes on it. By doing that, it won't be able to use the index on department number, even though it exists. In the view itself, there are no predicates using it, so we can't use it when we do here, and the result table doesn't have any indexes on it. So we can't use it when we call the defining query, and we can't use it when we call the query on the view. But by merging this by pushing the predicate into the view, then we can do it. So we want to limit the columns. We're only getting one column from the tables. And what we're doing is rewriting it. We just basically take the union, drop it in as a inline view, and then we add the predicate to us. We can push this predicate down to each leg. Joining them both together and just getting and then limit it to department 20 is the equivalent of limiting each of them to department 20, sort it to get rid of duplicates. Okay, and with the e-name there may be duplicates. Okay, but we want to do this. Okay, so we push down the predicate to each side. Now, which is better? This just opened up the opportunity of using an index. The way we do it here, we'll have to do a full table scan on both of these to create the result set, and then do a full table scan because we have no indexes on the result sets to apply. Now, when we scan these two, we now opened up the possibility of using the index if we have an index on department number on both sides. So it will cost the both of them, and which one is cheaper, it will make the decision to use that. Okay. Next one is an interesting one called transitivity transform. We have an original query where we're joining the employees to the department table. It's an equal join between the employees and department. Okay, whoops, got the wrong condition in here based on the department number. And then we have an additional filter that's going to reduce the data. Okay, because we don't have an index, okay, on the employee's department number, we can't use it to filter the data, because that may help us pick the employees table to filter, but this is a foreign key. We do have one over here generally because it's a primary key, so we might be able to use it as the join, but we can't use this one. We don't have an index on this one to filter it additionally. Okay, if these two are true, department number for the employees has to equal department number in the department table, and a department has to equal 20 on the department. It implies a third condition is also true by transitivity. It implies that the department number also has to be 20. We can add that condition without semantically changing the query, but by adding it, it now opens up the possibility of using an index. And the optimizer will try that as a transform to see if it's a lower execution cost than doing it without using the index on the department number. Okay, equals a particular to filter the data. There are other possible solutions to it. I mentioned earlier, one of the things that a lot of applications do is a foreign key to primary key join naturally. We put an index on the primary key, we don't put a 1 on the foreign key. A lot of applications could take advantage. If we put the index on the department number, then we would have had an index to use this to filter the data. Okay, so that would have solved it. Another change, since we know by transitivity that this is the same as saying that department numbers equal 20, if we had coded it as department number equals 20, then we could have took advantage of this index without doing the transform. Sometimes there is more than one possible solution. The one they looked at is what the optimizer will try without you changing the statement. The other two would require you to write the statement, but as we mentioned, how we write it can influence the options. The optimizer, and putting an extra index on foreign keys tends to be a good thing generally for applications in a lot of cases. Hints for query transforms. The following hints instructs the optimizer to use a specific SQL query transform. And there are a group of these. As I mentioned, we don't look at all 100 hints, but we look, because we're looking at the transforms, we'll take a quick look at these. The first one is no query transform. I just don't want to do a query transform at all as I process in the statement. The second one is use concatenate. Okay, the use concatenate hint forces the combined ORs conditions in the where clause to be transformed into a compound query using union alls with the and conditions on them. So it can transform them. Normally it will try this and pick the lowest cost. Okay, if you specify no expansion, it prevents it from doing the use concatenation type expansion, and it also limits one other. Okay, it also disables the in-list processing, specialized processing for it. So it's actually does more than one thing, just like query transform turns off all the transforms. This enables one, this disables two of them. You just got to get used to what they do and check the documentation. This one is really for materialized views. It's just indicating if you do happen to it, and we saw it in lesson 4, materialized views can be good things for large reports and data warehousing applications. Okay, you can control with hints whether or not we rewrite to a materialized view or not. Rewrite says, I'd like you to do it. For this statement, no rewrite. So once again, very useful for testing things, I find. Okay, you can also hint on the merge, no merge in your particular environment. Okay, the merge lets you merge a view for each query with the query, so we get a different execution plan. Sometimes it opens up indexes. Okay, the no merge causes it not to. Complex merging is not cost. Okay, the accessing blocks must include the merge hint. Without this, with normal cost optimization, it doesn't try the complex view merging unless you give it the merge hint. It will do the simple merging. You can also turn off all merging by saying no underscore. A lot of these have the equivalent no underscore version that negates them. Okay, if you're into data warehousing, okay, which we suggest you read the data warehousing documentation, and we have some very nice data warehousing courses that looks at issues for data warehousing. But the star transforms are disabled on a database by default. It needs to be enabled, and then we can enable and disable it for a particular query. Star transform says do the optimization for doing star queries. No transforms don't do that optimization. When you're using the star schemas, you can also hint on a fact table. Say the fact table is sales. We saw an example of that in lesson 4. You can also do a more general hint that's if it's trying to use another table as the fact table and it's got the wrong one. Sometimes this occurs in a cluster where we're combining multiple areas in a data warehouse and there are actually more than one fact table, it gets the wrong fact tables for some queries, we can say no fact on one of the other tables. And it's actually a little more general. The less we can hint at to get it the way we want to do it, the less maintenance generally. We can also hint on doing nesting or unnesting, okay? When we hint on the unnest hint, instructs the optimizer to unnest and merge the body of subqueries into the body of the query block that it contains, allowing the optimizer to consider them together as part of finding the access paths. When it can't unnest them, quite often it has to treat them as independent blocks that aren't related. So you can say, I want to unnest the subquery, if it's technically possible, or you can say, I'd like to cost it without the nesting. Have a look at its performance. Okay, so we have a quiz coming up. Okay, the quiz question is, the view merging optimization, which is the normal optimization during a normal look at doing a merge transform, merging the outer query with the select that defines the query, applies to views that contain only selections, projections, and joins. In other words, simple views. Is this true or false? We'll give you a moment to think about it. And the answer is A, this is true. Complex views won't be merged unless you give it the merge hint. Non-complex views such these, the things that only does this. And a view without a join is also considered a simple view. We saw some without doing joins can be merged automatically as part of the cost-based optimization. Complex merges normally aren't considered by the optimizer today unless you give it the merge hint. Okay. Second question. We got a little query out here we want you to review the following query. What we're doing is a inline view that's joined with the product table with some additional filters on it, okay? And we're doing a equal join with an outer join on our query. So the plus indicates an outer join using our old syntax. Then we have a look at the execution plan. Okay, and we'll let you read through it for a moment. It talks about nested loop, full table access, view, push predicates, sort aggregate, etc. And it talks about a local index row ID and a bitmap index access path. So we're using a bitmap index. And over here in the names, it just shows you the names of the index. It was a sales product bitmap index. And the table, we were using that to access the sales table. And we have the products table. The sales table is part of the inline view. The products table is what we're joining the inline view with. Now we have some questions based on what we've talked about so far in this statement. So the first question is, A, has a query transform taken place? And we want to know which one of these are true or false, which is true. A query transform has taken place. So let's go back and take a look at the execution plan. In the execution plan, we see view pushed predicate, which is one of the transforms we looked at. We talked about pushing the predicates. So we took a view, the inline view, and pushed the predicates into it. So that's a transform that was done on the inline view. It wasn't a view I created. As a view we stored in the data, it was the inline view that was written on a query, this subquery up here. And we pushed the predicates up here into it. So yep, a transform did occur. Next up, the optimizer considers a nested loop join when P and V views are joined even with the group by clause in the view. So what can we glean from this? Well, it considered a nested loop. In fact, it chose a nested loop because the nested loop was mentioned as the second line in the execution plan. So when it joined the two, it actually did it as a nested loop. So yep, it had to consider a nested loop to pick it. Third question, so B is true. C, the optimizer considers only two possible join methods, the hash join and the sort merge joins tables B and V. Well, to really see what it considered, all we know it picked a hash join. But generally, as long as it's technically doable, it considers all three. And we know this one is incorrect because the method it's picked was neither of these. It did it as a nested loop. And so it had to consider the nested loop also for it to be picked. So it actually considered all three. Okay. D, so C was false. A and B were true. Okay. D, a join predicate pushdown has become possible, and you are now taking advantage of an index on the sales table to do the nested loop join of a hash join. Okay. And you do a nested loop instead of a hash join. And that's true. We saw it use the bitmap index on the sales table as it was used in a nested loop to join it. So D is also true. Next up, we're going to talk about another switch topic and talk about another interesting topic, how we estimate selectivity and cardinality, and how important they are as part of our processing an SQL statement. So, selectivity and cardinality. Selectivity is defined as the estimated portions of the row set retrieved by a particular predicate or combination of predicates. It can be calculated if we know the total number of rows that satisfy a condition and divide it by the total number of rows in the table. So if we have a predicate on a column that says we're looking for employees in a certain city or in a certain department, if we know the number of employees in that department divided by the total number of rows in the table, then we can get an accurate calculation of selectivity. Okay. The next thing is cardinality. Cardinality is the expected number of rows retrieved by a particular operation in the execution plan. And the cardinality can be calculated from the selectivity using the formula we show here. Cardinality equals the total number of rows in a row source, or if we're at the bottom of the tree looking at a table in a table, times the selectivity of the predicate. Okay? If we have an accurate, exact calculation of selectivity, you can go back and forth. But generally, we don't have an absolutely accurate value. We use an estimate in a lot of cases. The selectivity is expressed as a value between 0 and 1. Okay, 0 says it's very selective. In fact, it acts as a wall, doesn't pass any rows through. 0.1 will do 10% of the rows. 1 is it passes all the rows. So a high value for selectivity, which we call high selectivity, returns, which is closer to 0, returns a few portion of the rows. The closer it is to 1, the bigger portion of the rows it returns and the lower we consider the selectivity. Okay. And it likes rows that have high selectivity, really filter the predicates that really filter the data a lot. We can reduce the data quickly. The earlier we can reduce more data, the cheaper it is to process the statement. And how do we get selectivity if we don't have an exact computation? If there are no statistics and you create a new database, dynamic sampling at parse time as an optimizer feature is turned on automatically for the database. It will use dynamic sampling. If dynamic sampling isn't available and there are no statistics, okay, that are usable, then there would be, if there were no statistics at all, then there would be no histograms, which means we assume a normal distribution, okay, which means all values are equally likely. So if we have a table with a column with two values, A and B, and those are the only values for 1,000,000 rows, we expect, if it's normally distributed, half will be A and half will be B. That's not very selective, it's right in the middle. We would like it to be a little closer to 0. Not 0 usually, but a little closer to it. Okay. If we have a 1,000,000 row table and we have 10 values, then we expect each of them to be 100 million, okay, for our table. If that is not true, if one value has 2 rows and another value has, 2 others have 250,000 each, that's non-normally distributed. A histogram will give us the best information we possibly can get in a lot of cases, okay? If we've collected statistics, if we did a compute of the statistics, we do an actual calculation for each of them. But it's very expensive to do that for large tables. We have to grab the data of the table, sort it, and do the calculation. If it's 100 million row tables, we probably don't want to do that all the time. Generally, we find if we can get the good statistics with a lot smaller subset, somewhere in the order of 5 to 10%, and calculate the selectivity based on that sampling, will give us a good view of the data generally. Why are these important? Well, the selectivity estimates influences our estimate the I/O costs for a particular operation. It also affects the force cost. The more rows we have to sort, the more expensive it is generally. And the bigger the rows they are, the more expensive. Cardinality is important in determining the join method, the join orders, whether a filter reduces the data enough to make it worthwhile using an index, and the sort costs. If incorrect selectivity and cardinality are not used, we're giving it bad choices for the execution plan. We won't get the best execution plan. It will miscalculate the costs for different things. So original cardinality, selectivity, but we really use computed values for them. And we use them to determine the cost and eventually come up with a costing of the execution plan, generally. Good input equals good output. So this is an example taken from our customer table. It has, we've seen already, 55,500 rows. That's the number of customers we have. The number of distinct values for customer city is 620. The number for provinces is 145. The number for distinct values, unique keys for the country ID is 19. When we go in and have a predicate, we can calculate the selectivity of each of these predicates individually. So, and then we calculate the total selectivity by taking the selectivity of each of them and assuming each of them filter the data the same amount, we just multiply them. So what is the selectivity in the where predicate? Okay, and we'll calculate that.